Okay, so here we see, we ask a question whether this, again, mathematical formalism for the description of the forces applied within a continuum using a tensor is consistent with the conservation of angular momentum. And what we'll do is we'll assume the same, we have the same view. What if we look at a control volume which we shrink to a single point? And what you find, again, when you write in conservation of angular momentum in this case, is that the equation of conservation of angular momentum reduces to a single term, which is the dominant term, and which is the integral of the torque due to the stress vector. So there will be the integral along the control surface of the position vector, cross product, the stress vector, and this integral should be equal to 0 if we're integrating again on an infinitesimally small control surface. Alright, so here to simplify, I'm going to look again at a simplified small surface, and I will only look at it in 2 dimensions, but this is fully general. You could look at it in 3 dimensions and it wouldn't make a difference. But let's say that our control volume in 2D is a simple square, and think of this of a 2D control volume. And so we have 4 control surfaces here: a surface of normal x, y, minus x, and minus y. Again, so this is really what I'm thinking about, is a control volume really, which will look like this. Right, so it is a volume, and this will be the surface of normal x, but I'm just projecting it on the xy plane because we don't really need to look at it in 3D. Okay, so on this surface, the force exerted by the continuum on this side of the control volume on the material on this side is a stress vector. So this is our stress vector T of normal x, and on this surface, for instance, it would be the stress vector, doesn't have to be the same, T on normal y. And because we reduced it to a point, note that the stress vector that we would have on the other surface is minus T y, and same for the surface of normal minus x. And so if we take the stress vector T on the normal x, this is equal to x dot our stress tensor, and here our stress tensor will be a 2 by 2 tensor. And remember that the vector x here is the vector 1, 0, and therefore our stress vector here is simply, so the component of our stress vector here is along the x direction. This is T x x. So this vector here, the stress vector, is equal to this vector plus txx plus txy. Now I want you to note directly here, when you write the stress tensor in this way, then the first symbol, the first index here, this x here represents the direction of the normal. Right, so here we're looking at the stress vector on a surface of normal x, and then the second index represents the direction of the vector. So this is the x component, and this here is the y component. Okay, so given that, if we look at the torque, which is generated at the center of the control volume here because of the stress vector on the surface of normal x, then we find that the lever arm here is the half of this length. Let's call it delta x divided by 2 times this component of the stress vector, so that would be txy, and we integrated over that surface here, so that will be another dx, delta x. Now we can do the same for the stress vector on the surface of normal y, and the vector y is 0, 1, and therefore what we have is the vector tyx, tyy. Again, the first index here represents the direction of the normal, so this is the surface of normal y, and the second index here represents the direction. This is the component, so this is the component along the x direction, this is the component along the y direction. This here is tyx, this component here is tyx, and that one here is tyy. Okay, so if we look at the contribution, the torque contribution to the angular momentum equation of this surface here, it will be this lever arm here, again a delta x divided by 2, times tyx, but now the torque is going in the other direction, so that will be minus delta x divided by 2. The only force component that contributes to the torque is the tyx, not the tyy doesn't contribute, so tyx multiplied by the surface here, and that is still a delta x. We assume we have a square. Okay, and then if we look at these two surfaces, well, I'll let you do the math, but you see that this adds another delta. It adds the same term as this one here, and that torque here again is a torque in the other direction and adds the same as here. So essentially, if we account all of the other surfaces, the two other surfaces, we get a 2. Right, and here, if we want it to be consistent with conservation of angular momentum on a infinitesimally small control surface, that has to be equal to 0. All of these cancel, and in the end, what we are left with is that t xy, if this tensor notation is consistent with conservation of the angular momentum, then txy has to be equal to tyx. That is to say that our stress tensor has to be symmetric. And so for this we deduce that we can represent indeed the state of stress at a single point with a tensor, right? And that would allow us to represent what are the forces imposed within the continuum with a matrix, which we call the Cauchy stress tensor. And this Cauchy stress tensor is always a symmetric tensor. And again, the symmetry is because this is in order to be consistent with the conservation of angular momentum. Now, first remark is, if you may recall from your linear algebra, that a matrix which is symmetric can always be diagonalized in an orthonormal base. So T is symmetric and therefore it can be made diagonal. So some terminology, the stresses which are along the diagonals are called normal stresses. Those are stresses which are those corresponds to the component of the stress tensor, which is in the same direction as the normal direction. So these here are the normal stresses, and the off diagonal terms here are called shear stresses. And because this matrix is symmetric, it can be written in a given orthonormal base. It can be diagonalized, and so when we diagonalize it, then we only have normal stresses, and in the base in which the stress tensor is diagonal, we call these stresses here the principal stresses.